Extensive efforts to minimize energy consumption have enhanced efficiency, reducing losses and significantly lowering carbon emissions, an essential consideration in component selection. Power supply solutions are crucial, as nearly all electronic devices depend on AC to DC or DC to DC converters to function effectively. This video will explore the following topics: the link between efficiency and losses, methods for calculating efficiency, accurate measurement techniques, interpreting datasheets and derating curves, and key factors affecting efficiency. Power converters inherently generate some losses, and their efficiency is determined using a specific formula. Efficiency is calculated as the ratio of output power to input power, typically expressed as a percentage. Input power equals output power divided by efficiency. In a converter, input power minus output power represents the losses. To calculate losses, use the formula: losses equal output power multiplied by 1 minus efficiency divided by efficiency. The explanation feels overly complex with too many formulas. Let's simplify it with a practical example. Suppose we have a 24-volt battery as the power source, and the load requires 12 volts and 100 watts. Based on the datasheet, the power supply operates at 94% efficiency. In this example, the input power is calculated as 100 watts divided by 0.94, resulting in 106.4 watts, with the converter experiencing 6.4 watts of power loss. Efficiency is accurately measured by power supply manufacturers using a specific setup to evaluate DC-DC converters. Precise voltage readings are taken directly at the converter's pins to ensure reliable results. The setup for AC to DC power supplies is comparable and typically involves using a true or RMS power meter. Efficiency is not fixed. It varies based on operating conditions like input voltage and output voltage. Different efficiency values for a converter are listed in the datasheet, typically measured under specific input, loads, and environmental conditions found in product overviews. The 94% efficiency is achieved under nominal input conditions of 24 volts, a full load of 100 watts, and an ambient temperature of 25 degrees Celsius. How to get the efficiency values for other operating conditions? Graphs in the datasheet can be used to determine efficiency in specific operating conditions. This graph shows the efficiency curves of a 24 to 15 volt 100 watt converter for 150 and 25% load, and as a function of input voltage. Another graph shows the efficiency curves for different input voltages as a function of the load. For additional details or specific values related to your converter and applications, please reach out to P. Duke's application engineering team. System designers should remember that overall system efficiency is influenced not only by converter losses but also by other factors. Additional losses stem from wires, PCB traces, connectors, fuses, EMI filters, and decoupling diodes. To maximize overall efficiency, these losses must be carefully accounted for in efficiency calculations and measurements. Efficiency can be summarized as follows. Every energy conversion process involves some losses. Efficiency is calculated as the ratio of output power to input power. Losses in a converter are determined by subtracting output power from input power. Additionally, other components can impact the overall efficiency. For further inquiries, please contact P. Duke's application engineering team through sales.